Is that better?
So it's my pleasure to introduce Carlos Arreche, who will speak about differential transcendence of elliptic functions through Galois theory.
Thank you very much, and thank you for the invitation. It's a real pleasure and honor to be back here, where in some sense my math journey started or kept going. I'm very happy to see all of you again. So what I want to talk about today is an application of Harouan and Singer's differential Galois theory for linear difference equations to these objects called elliptic hypergeometric functions. In past iterations of a talk covering the same material, I wasn't sure what to say about these functions because they came from the mathematical physics community, so their importance and what they are all involves things that I'm not an expert on. So the first few times I said, well, they care about them, moving on. And for you today, I felt that I should say something more about both why they're important and how they're defined, as best I understand it. So before I go on, this is joint work with Thomas Dreyfus and Julian Roch, and this paper has been submitted, and if it's accepted, then you'll know where. But right now, if you want to read it, it's from the archive, and here's the number. So first, let me tell you my best understanding of why the mathematical physicists care about these functions. So these are some relatively recent special functions that until the early 2000s, they did not appear in any of the usual list of special functions. I've never seen a definition of special function written down, but my understanding is that they are the pretty ones. Out of all the functions that you could think of writing down, well, these are the ones that you would be able to write down and that have nice properties.
You know, but the name sounds very classical.
Of elliptic hypergeometric functions.
And you're saying that's just
yes,
recent thing.
it has classical sounding in it, but they hadn't been put together in just one notion. Thank you. So indeed, these are analogs. They are both analogs and strict generalizations of the classical Gauss hypergeometric functions, but they are related to elliptic curves instead of just some parameters A, B, and C. So the applications that they have found are in representation theory and parts of representation theory connected to mathematical physics. They believe, but as far as I know, they haven't shown that because of the analogies in the construction of the functions, they believe that they should be related to certain parts of representation theory in the same way that classical hypergeometric functions are related to other parts of representation theory, and that connection so far is conjectural. They've been trying to get traction there, but that work is not done. They've also found applications to the parts of representation theory that they have been able to work out to what are called four-dimensional supersymmetric quantum field theories. And I think I understand about half the terms here, but not what they mean when strung together. But still, here they are, in case they do mean anything to you. And then, apparently also, they find connections in what are called exactly solvable models in statistical mechanics, which again, I'm not an expert in this area. I took this list from a survey article on the theory of elliptic hypergeometric functions, and this is for the benefit of people who do understand this better than I do. So before I get to saying things formally, what we have been able to show is that, together with my co-authors, Thomas Dreyfus and Julian Roch, most of these elliptic hypergeometric functions don't satisfy any any algebraic differential equations with elliptic function coefficients. So we've, this most here ought to be in quotation marks. Our result is a bit more precise, saying that in some reasonable sense, most of them don't satisfy differential equations follows, but we actually have a concrete criterion in terms of which elliptic hypergeometric function you're looking at that guarantees that it does not satisfy any differential equations.
I have a question. What is the connection between the problem that you are solving and how they are found in applications?
This I'm actually not sure about, partly because I have very limited understanding of what the applications are. But I am going to meet with a bunch of these people, including one of them who's named later on this summer in a country, in Sweden. And when we posted our article on the archive, they somehow saw it and got in touch with us, and they were about to have this nice conference talking about these things, and they wanted to hear about it. So I think that that's going to be a very productive interaction, where I'll learn a lot more about both what their stuff means and also how our results might be connected to things that they care about. So in the survey, they do list all the things that they have been able to prove about these special functions, but of course there's no list of the things that they haven't shown, and this is a new one that they didn't have yet. And we'll see, frankly, whether they care, and if they do care, why. So let's talk after the summer and let you know.
Sounds good.
Okay. So now that I've told you as best as I can why these things are important, at least to this community, I want to get as close as possible to defining what they are. I won't write down an explicit formula because it looks messy to me, and in any case, I can't explain it. It's just a big expression, and I figured I shouldn't put anything on the slides that I don't know how to explain to you. But I'll tell you as much as I feel comfortable telling you. So first, let me tell you a little bit about theta functions. These are going to underlie both how the elliptic hypergeometric functions are defined, and then also how we were able to prove our result about those special functions. So these are analogs of the, sorry, not analogs. They call this version of the theta function a modification of the Jacobi theta function. It's similar, but some factor in this definition is missing from the original one. So the way that you define it is defining first this infinite product, and then the theta function itself is defined as a product of things that look like this. And the main property that I want to concentrate on is that from the infinite product expression, this whole infinite product is going to vanish exactly when the argument is an integral power of z. Also, the theta function is not p-periodic. I'll get to that definition in a second, but let me point it out now. Being p-periodic would mean that when you modify the argument by multiplying it by p, the function stays the same. This one does not. However, somehow it still makes sense to talk about what a zero is in the elliptic curve defined by p. So we'll get to this in more detail, but I wanted to point it out now. Is there a question or comment? I'll take that as a no.
Yeah.
Okay. So let me first tell you what these p-periodic functions are in terms of theta functions, and we'll come to those later, and then I'll tell you how they're used to eventually define the elliptic hypergeometric functions. So like I said, meromorphic function on the punctured complex plane is p-periodic exactly when multiplying the argument by p doesn't change the function itself. So the field of p-periodic functions on C star is actually identified with a field of meromorphic functions on this elliptic curve given by taking the quotient group of C star modulo the subgroup of integral powers of p, and this quotient ends up having a structure of a one-dimensional complex manifold, and it's an elliptic curve. So probably if you've heard about elliptic curves before, and the multiplicative notation is a little bit more unusual than the standard one, so let me briefly tell you how the two languages are related. There's this a standard dictionary that just because it's standard doesn't mean that everyone's familiar with it. So if you're used to thinking of elliptic curves as coming from quotienting the complex plane itself by a lattice, then if this is your lattice, this map where you exponentiate the function c to send it over to a local coordinate on C star induces an isomorphism between the way that you want to think about elliptic curves and the way that I have to think about elliptic curves, because this is the language that is relevant for the elliptic hypergeometric functions. Now, one of the reasons why I wanted to tell you about theta functions first thing is that because of the functional relation that they satisfy, the theta functions themselves are not p-periodic, but any quotient like this will be p-periodic, and not always, but you do need these coefficients modifying the theta functions to satisfy the so-called balancing condition. And what's going to happen is that if you stare at the functional equation, transform this, try to modify this whole thing by changing z to pz, these aj's and bj's are going to come out together with some z inverses, and they're going to cancel exactly because you have the same number of them and this equation is satisfied. Okay. So this balancing condition here is what forces a product of this form to happen to be p-periodic, and later on we're going to see a different kind of balancing condition whose job is exactly to make sure that a certain thing happens to be p-periodic also. Yes?
So this function, so for each c you get one of those functions.
Yes.
And they all different?
That's a good question. I don't know when they're all different. In fact, I know that they can't all be different. Let me tell you why. So,
Why isn't something different?
A meromorphic function on E is essentially determined by what its divisor is, together with what its value is at some point. So because the theta functions, when you give me a p-periodic function in this form, I can exactly write down what its zeros and poles are on the curve with multiplicities. But the theta function itself, it has zeros on C star at all the integral powers of p. And so you could shift it and end up getting the same set of zeros and poles down in the curve. So those functions down there would end up being the same. So this expression is not unique, but whenever you have an expression like this, you can explicitly write down the divisor of the meromorphic function. And that's actually going to be the main use that we get out of expressing p-periodic functions in terms of theta functions. Thank you for the question. Okay. So now I want to use the theta functions to first define what are called elliptic gamma functions, and then those are going to be used to define finally the functions that we care about, the elliptic hypergeometric ones. So at first you define some kind of infinite product that's similar to the one used to define the theta function itself, but now it has two different, the old p and then also a q, and it's defined in this way. So this is going to have, I didn't think about what the zeros are, so let me not tell you. But it's essential that that q, you're assuming this for p as well, that its absolute value is smaller than 1. And then I'm also assuming that the set of integral powers of p and q is as disjoint as possible. Okay. So I'll tell you later a little bit about how to interpret this condition in terms of what kind of point Q defines in the quotient elliptic curve. But having this infinite product, you define the so-called elliptic gamma function in this way. I read in the same survey article that this elliptic analog of the gamma function has been around since at least 1972. And the reason, if you like, why it's called an elliptic gamma function is that when you modify it by shifting or multiplying the argument by p, what you get at is theta of zq, and if you like, again, theta is not it's not elliptic, but its set of zeros on the elliptic curve is still well defined, and this is like the local variable centered at the identity of the curve as far as the divisor goes. So the modification rules for the gamma function mimic to some extent the one satisfied by the all gamma function, where instead of multiplying the argument by something, you're shifting it. And when you shift the argument, you get again that the gamma function is modified by multiplying it by the function that has a 0 for the 1 at the identity of your group. Okay. So that's why it's meant to be roughly analogous. And now it's a classical fact that the classical Gauss hypergeometric functions can be expressed in terms of the classical gamma functions. Sorry, there's just the one gamma function classically, and there are in fact several integral formulas relating gamma functions and classical hypergeometric functions, and the one that's meant to be analogous for us in the next slide is the one that's called the Barnes integral formula. This is a part where if you ask me to write it down, I can, because I brought a copy, but if not, you can just look it up later. Do let me know if you want to see it at any point. Okay. So now finally, just like the classical hypergeometric function depends on these three parameters, a, b, and c, the so-called elliptic hypergeometric functions are going to depend on 8 parameters, and I'll need them to satisfy this balancing condition, which looks different from the one that we had earlier in trying to express p-periodic functions in terms of theta functions. But again, we'll see shortly that its job is still to make sure that something else happens to be p-periodic.
The epsilons are what kind of quantities?
Oh, gosh, they belong to C star. Thank you. Sorry, I should have written this down. Okay, and here's what I'm skipping right in the formula because it's big and I don't even know how to read it. But the point is that the formula defining exactly what the hypergeometric functions are in the elliptic setting are analogous to the more classical Barnes integral formula doing the same for the classical hypergeometric functions. Okay, so there's an explicit expression for them. And now I can tell you a bit more specifically what I mean by saying that most elliptic hypergeometric functions don't satisfy algebraic differential equations. The most is contained here. So these parameters epsilons together with the p and q, they have to satisfy some kind of equation. So they're not multiplicatively independent, but if they are as multiplicatively independent as possible, in the sense that this is essentially the only relation that they satisfy, then whenever that happens, the corresponding elliptic hypergeometric function will be differentially transcendental over the field of meromorphic functions.
So just you generate these relations only multiplicatively, right? So basically what you say is that every relation is certain power of relation 1.
Precisely.
Okay, only powers, so it can be checked easily, right? If I given a relation, whether it's induced by 1, I can check just see whether it's power or not.
Can be checked easily. It depends on how the epsilons were given to you. So we're trying to do algebra on analytic objects. So if you mean checking by computer, it depends on how well you know your epsilons.
Yeah, I see. But if I'm just so let me reformulate. If I'm given a relation, and I want to check whether it's induced by one, right? I given it symbolically, like epsilon 1 to the fifth
right.
times epsilon 2 to something. It amounts just to checking whether it's power of 1 or not.
Yes, exactly. So so you have to decide whether if it's a symbolic expression, some product of the epsilons and the p's and the q's being equal to 1, then I want all the powers of the epsilons to be equal, and then the powers of p and q to also be equal to each other and to be equal to negative twice whatever the powers of the epsilons were.
Okay.
That's exactly what I mean. Yeah.
So what multiplicative relation means integer powers, positive integer powers, whatever.
Just integer powers. Thank you. So
So you allow negative powers.
yes.
So this is so you're looking at the multiplicative group generated by the epsilon.
Precisely, and I'm asking that it have a presentation given by exactly this equation.
One more question. So, just if I'm thinking in terms of usual elliptic functions, so usual elliptic function, it's always expressed with the Weierstrass function and its derivative, right?
Mhm.
So this means that every elliptic function, standard elliptic function, is differential algebraic over C.
Yes.
Is it true for your elliptic functions?
The elliptic hypergeometric ones.
Yes. Yes.
No.
My question is, can I say that this is equivalent to differential transcendence over C?
It implies it in particular.
Yeah, it implies.
Because of what you said.
So it's equivalent.
I think. I suppose so. Let's see. So because they're differentially algebraic over this guy, which is differentially algebraic over
C.
the rational functions, then I get that implication that way.
Mm-hmm.
And the other one's probably fine as well. But what would the converse be?
No, I mean, just my question is whether this theorem is equivalent to theorem whether mere E is replaced with just complex numbers. I mean, of course, this sounds stronger, but basically, this is the same fact, right?
Yeah, I suppose so. Because of the observation that Mary is already differentially algebraic over the downstairs. Yeah.
Okay, I just want to clarify.
No, thank you. That's a good point. I hadn't thought about saying it that way.
So the multiplicative relation condition, that's a condition on the free group multi relation?
Precisely. Yeah.
Okay.
When I look at the abelian group generated by the epsilons p and q, I wanted to have a presentation consisting of exactly this equation and nothing else.
Right. You can't change the representations. Is that correct? So I mean, epsilon and PQ are all just given, right? Already.
For each choice of tuple
Right.
satisfying this condition, then this elliptic hypergeometric function is defined.
No, I just want to understand the multiplicative relation statement there. So you got a free group generated by some generators and this relation, but that group itself could be the same for different sets of parameters, epsilon, p, and q.
Absolutely.
Right.
Right.
And so when you say that that statement hypothesis there, you don't allow a change of the free group generators or more, some similar relation.
The theorem applies to any choice of parameters simultaneously, provided that the abelian group generated by them and the p and the q as an abstract abelian group has this presentation.
What happens if you
So you don't exclude other presentation.
Sorry?
You don't exclude other presentation.
No, I just need that
That particular.
yeah.
Okay.
But it's all particular ones, such that. Sorry.
So what if you replace E by C?
Elliptical.
I don't know. Just haven't thought about it.
Yeah.
Maybe that there might be too many more functions on C, and I just don't know. I mean, somehow mer E a priori seems like a messy analytic object. In fact, it's it's a function field of transcendence degree 1 over the field of complex numbers, and for the resulting Galois theory that we then use to prove our application to the special functions, you need your base difference differential field to be nice. And so if it's a crazy analytic field, I think that we just don't know what to say in that case.
Can I just put my question slightly differently?
Sure.
So suppose you have a group, this thing generate one group, let's call it G.
Mm-hmm.
But if you give a different set of representation with different epsilon, 8 epsilons and one and another P and another Q, would the epsilon Z be the same or not?
Would the
function that you defined as elliptic hypergeometric function?
Oh, it would be a different function.
It would be a different function.
Yeah, every different choice of epsilons and a P and a Q satisfying the things gives you a completely different.
So you are saying that the group doesn't give you any equivalence on the functions?
No, I mean, who knows? But I have no reason to believe that.
It's
that
an obvious equivalent relation, right?
Yeah, I mean, it might be that. Look, even in the case of the classical hypergeometric functions, there are all these different ways of twisting the parameters around to get different ones.
Right.
And
but that's the problem, right? The whole thing that we are trying to find out is what are the equivalent things.
right, and we don't touch that at all, and we don't even. Not only do we not know how these different things are related to each other, but we don't need to know. So it's somehow a selling point for the Galois theory that the proof that we have doesn't require us to know anything about what the functions mean or where they came from. In fact, when we proved it, we didn't. I looked this up just for you. And the Galois theory is nice enough that just because a certain thing happens, you get consequences. And later we think about what you got.
But see, I'm more interested in the symbolic computation. That in a hypergeometric function, even you get so many representations of the same function, basically. So why can't we just have some kind of a normal form? So if we have some equivalence like this, which is an obvious equivalent relation, right, by the group, I think, right? Yeah.
Okay. Right. So here's the results. I can't remember what slide comes next, but we'll find out at the same time. Okay, right. So that's all I wanted to say in general about the elliptic hypergeometric functions. And now I want to tell you how come I get to apply difference differential Galois theory to them. So the starting point in trying to apply this theory is having a base difference differential field. So let me tell you exactly what that's going to be for me. I'll point out again that my P and Q are non-zero complex numbers, and I demand that they have absolute value smaller than 1. They impose that condition for analytic reasons. And then I also ask for the set of integral powers of P and Q to be as small as possible, so there's only 1 in that intersection. I just want to point out now that this condition is equivalent to asking that the point on the elliptic curve defined by taking Q modulo P to the Z, for that point to be of infinite order in that abelian group. So my base field, as you might have guessed by now, is going to be the field of meromorphic functions on the curve. The difference operator is given by shifting the argument by this special Q. And so this condition that Q have infinite order gets translated into asking that the operator sigma be an automorphism of infinite order. And that's important in the Galois theory and in difference algebra in general, because when certain things break down when you have an automorphism that's only of finite order. And then my differential operator is going to be written explicitly as just z ddz. And with these definitions, you can check from the chain rule that sigma and delta commute. And so I get to do differential Galois theory over this base field with this structure. So I feel like this is the last place where I should have to tell you what these Galois theories are, but it would be wrong not to. So here we go, just briefly. If you start from a differential field with delta closed constants, this is a condition that's never satisfied in nature, but it allows you to carry out Galois theoretic arguments more naively by looking at actual groups of matrices as opposed to thinking about the functor that corresponds to them. And for this kind of result, and this is more or less a theme in this kind of application, this requirement doesn't really get in your way very much. So there's a way to modify the base differential field so that you can get away with assuming that this is differentially closed, and then it turns out that the questions that you need to answer can be answered already over the field before you took the differential closure, and everything's fine. It's just fine. Okay, so starting from a linear difference equation, I get so-called sigma delta Picard-Bessel extension, which plays in this theory the role of a splitting field in classical Galois theory, where it has as many solutions as possible. It's minimal with respect to that property, and I forgot to write that the sigma invariants of R should be the same as those of K. Okay. Because you've seen this before, and then if you haven't, it's not worth dwelling on it. I'm being a little bit lazy with how I write what the R is. There's just something that plays the role of a splitting field, and what I did not write is that you should also adjoin to R the inverse of the determinant of the Casoratian matrix. Okay, so now the sigma delta Galois group is going to be a priori defined as the group of K algebra automorphisms of this ring that respect both the difference structure and the differential structure. So that's how come the Galois group is able to tell you anything about what kinds of differential equations your solutions satisfy. But then the choice of a basis of solutions identifies this abstract group with what's called a linear differential algebraic group inside of GLNC. So for the next slide, also think that you've all seen this before, but it would be wrong not to say anything about it. So let me tell you briefly what a linear differential algebraic group is, and at the same time call your attention to something that we'll need later when I'm trying to sketch the proof of our main result. So what I mean by a linear differential algebraic group over some differential field is a group of matrices that's defined as a subset of GLN by the vanishing of a set of algebraic differential equations. So here are some examples. Any algebraic group over the field is already a differential algebraic group because polynomial equations are very special kinds of differential equations where the differential just didn't appear. A bit more interestingly, any algebraic group over the field of differential constants is a linear differential algebraic group, which is defined by the equations defining this algebraic group here, together with one more differential equation for each matrix entry that says that delta of it is 0. Quite a bit more interestingly, if you give me any linear differential operator with coefficients in the field, I can ask for all the elements in the additive group that happen to be killed by that operator. And because the operator is linear, the set of such things is going to be closed under addition. So here's the group, and it's defined by differential equations. Similarly, if I give you any element of the multiplicative group, and I demand that its logarithmic derivative be killed by some operator, well then the D-log formally turns products into sums, and then again the fact that things having this property are closed under addition at the D-log level and hence under multiplication at the GM level makes this into a subgroup that's defined by differential equations. So it's a cool theorem of Felix Cassidy from 72. Okay, that any differential subgroup of the additive group or the multiplicative group has this shape. Okay. So now, what's the what's the result that we proved within the differential Galois theory that allowed us to get this conclusion about the elliptic hypergeometric functions. Here, I don't want to write down the conditions, but we can talk about them later. I'll tell you for now that they're very mild, and a number of people have imposed them already. Maybe I'll say it out loud. You want K to be a C1 field, which is an algebraic geometric condition on this function field, and also that it not admit any finite algebraic extensions to which the difference operator extends. Okay. So in some examples, your base field actually doesn't have this property, but then you can go up to a bigger field that does and work over there, and then somehow show that you're still only working with a smaller field. Okay. Let me sweep that under the rug, but just to be honest, there is something that I'm not telling you. So now this result, which again applies not just for my special K of elliptic functions, but almost in general, so if you give me a non-zero solution of a second order linear difference equation, I can tell that it is differentially transcendental over the base field K, provided that these two things are satisfied. The first is that the so-called Riccati equation have no solutions. What this means is that the difference operator doesn't factor into first order factors in the ring of difference operators, or equivalently that the associated Galois group is irreducible. We'll come back to this later, but just for now. And then the second condition is that if you look at the logarithmic derivative of the such coefficient b, I want for there to not exist a linear differential operator, which when applied to that d log of b, ends up having this shape for some function h also in the ground field. Okay. So this kind of problem in multiple contexts has been heavily studied in the symbolic computation community. It's called a telescoping problem, and it just likes to come up a lot in all these souped-up Galois theories that have a few operators in them. Okay. It's a very common thing to run into. So if you can't find a U like this, and you can't find a telescoper like this, then that forces the solution to be differentially transcendental. So we have until 11:15, if I recall, right? Now let me tell you how come that I even get to apply this differential Galois theory to these funny new special functions that are defined using elliptic gamma functions, which, what does it all even mean? There's a theorem proved by one of the founders of this theory that the elliptic hypergeometric function associated to this choice epsilon of parameters epsilon 1 through epsilon h satisfies this functional equation, which I've written in a funny way because it looks symmetric and palatable. So let me point out two things about this equation. First of all, this nu that appears here is just a number. Okay, there are no z's in it. It's just a funny number, but still just a constant. And this function a of z, it is a bit of a mess. But what happens is that this balancing condition that I insisted on drawing your attention to earlier ends up forcing and actually being equivalent to asking for an a of z written in this way to be p-periodic. Okay. So the balancing condition that I have to have my epsilons satisfy ends up meaning that my elliptic hypergeometric function satisfies this difference equation over k. Then I'll also point out explicitly that even though this does not look a priori like a second order difference equation, it is, if you just apply sigma to it, you get a sigma squared appearing as the highest order, and it's still a linear relation amongst f, sigma of f, and sigma squared of f.
Is it a 6 or an 8 though? Second problem.
This is a 6.
It's a 6.
Yeah. I don't know why. I mean, somehow, even in the
I don't know whether it was a typo or not. That's what I'm asking.
no, it's a fair question. If it was a typo, maybe I would no. It's definitely not, and I did double check. As some kind of let me make a comment to enhance the believability that this is correct. Even already in the classical case of Gauss hypergeometric functions, there are three parameters A, B, and C, and they are not equal. C is different.
Now, the other thing is that the epsilon 1 to epsilon 8
Mm-hmm.
are not ordered in any way. Is that correct?
What I'm saying is that they are. They are not all in equal standing. The last few are different.
Epsilon 8 seems to be singled out here.
Yeah, and epsilon 7.
Oh, where's the 7?
Yeah.
Oh, that's a 7.
Yeah.
Sorry.
There is something funny going on here, and I can't tell you why the last few parameters are different, but I can tell you that they are because of what you observed. That they're not all in equal standing.
And where does the number 8 come from?
I don't know.
What? 2 to the 3. Ah, okay. Has that anything to do with these elementary particles and whatnot?
Or the octonions. I don't know. I really have no idea. But I wish I knew, so it's a good question. I just don't. Okay. So the reason I got to say something about these functions is that they satisfy a second order linear difference equation over K. And so now there's an app for that. I have a Galois theory that tells me things about this, and not just that, but we proved general results within sigma delta Galois theory in general that apply exactly to things that have a property like this one. So let me tell you why we got away with this in this specific example, and so you'll recall from the statement of our main result that I have to check two things. One, that for there not to exist a solution to the Riccati equation associated to the second order difference equation, and for that we applied earlier work of my co-authors Thomas and Julien that imposes conditions on the divisors. This is a formal integer linear combination of the zeros and poles with multiplicities of the elliptic functions, and in order to apply the criterion, in particular, we have to know what the divisors were, and because the coefficients are written in terms of theta functions, I can write down what the divisors are on the curve. Okay, so if we didn't have access to what the divisors were, we wouldn't have been able to test the conditions of the main result. Similarly, for the non-existence of the telescoper, we show that it doesn't exist, again by analyzing the divisor of this d log b, which we know. So it was essential that we knew it. And in showing that a U like this does not exist and a telescoper like this does not exist, the condition that the parameters epsilon and the p and the q were as independent as possible was essential. Now this is a feature of the proof, not of the fact. We don't know. Maybe all of them are differentially transcendental independently of what happens with these epsilons, but we don't know that. We were only able to show it in this case, but it seemed like a nice statement, so we should tell the world.
I'm still unclear about why the epsilon 8 can be singled out, because the condition is that the free group generated by epsilon 1 to epsilon 8 and p and q have certain general relation, and that relation is symmetric with the epsilon.
This is true.
So does that mean that the epsilon 8 could be, if I renumber the epsilons, then you can...
No, let me tell you that there's something there. So the condition that these things be independent, we brought it in order to apply the Galois theory, in particular for this kind of argument. But when they defined the elliptic hypergeometric functions, the last few parameters are different. And this already happens in the classical case. The classical hypergeometric function has three parameters, A, B, and C. And the parameter C is not like A and B. It shows up in different ways in the hypergeometric differential equation.
The definition of
Right.
epsilon.
Yeah. So the analogous, the very same kind of phenomenon that happens in the classical situation also occurs here. The last few parameters are like the C's, and they're not and they're not in equal standing with the A and the B in the like 2F1.
Bill's point about
Oh.
symmetric.
Sorry.
Bill's point about the relation being symmetric, though, is still correct.
Absolutely, yeah. Our condition doesn't tell the difference between the epsilons,
That's right.
but the function f does know that they're different.
So there are 8
And the difference
factorial-
equations
there are 8
actually-
factorial results then.
Sorry?
There are 8 factorial results?
No, there are uncountably many results.
No, of course, I mean, but given a set of epsilons,
Right,
there are 8 factorial permutations.
yeah, but there are
I
uncountably
mean,
many
so-
choices
I mean,
for the
you got 8
epsilons.
factorial different functions according to what they define, right?
Mhm.
Even if the groups are exactly the same.
Which group? Oh,
The free group mod the relation.
yeah, but it's
They're not determined by that condition.
I know.
no, right.
But
Right.
the result covers 8 factorial cases.
No, it covers almost everything. So if you
I
pick
know,
if
I
you
know.
pick eight analytic numbers at random,
Right.
they'd have to be extremely special for there to be additional discrete relations among them. And I'm saying that whenever that special thing doesn't happen, I can tell you things. You know, you would have to pick the last epsilon on purpose to make it be discretely related to the
Could I
others.
see the 2 conditions again on the, is it, oh, these are the conditions too, right? But
For the main
see-
results.
No, the hypothesis
Of the
the
theorem?
main result. Can you come to that
Hopefully
next
it's near enough.
slide? No, forward,
Forward.
yes.
Uh-huh.
No, back, right, this one. Is that this one?
There's an equation satisfied by the epsilons and the p and q,
Right.
and I want that to be the only equation satisfied by them,
So,
essentially.
But when you write the L, you got these, you said there are no C0 up to C8 or something, right? Did I read it wrong?
I'm not,
The L.
Two
the
slides
L.
ago.
2 slides ago.
Yeah,
Here?
Right, yeah, okay, Cn, right, okay. N being what?
N being anything.
N being anything.
I want for there not to exist any operator of any order playing the role of telescoper for this d log of b.
All right, thanks.
And I'm only able to show non-existence in each one of these cases by saying if a thing like this existed, I would be able to produce a multiplicative relation among the epsilons and the p's and q's that's not the kind that's allowed, so there can't be anything like this. That's the way the proof goes.
But that condition on the group is not a necessary and sufficient condition.
It's sufficient, but I don't know if it's necessary.
Right, so how can you go backwards to say that if it's not satisfied, then something else?
Oh, because I don't know what happens when the condition is not satisfied. No
I
idea.
thought that's what you just said, no?
No. We have a one-directional result saying that if there's no solution to Riccati and there's no telescoper, then it's different transcendental.
Okay.
But I don't know anything about the other way.
But you just said that if the first condition is not satisfied, let's say, then you can say, you can cook up some relations?
No,
No. You
No.
can't. Okay.
no. Saying that in our proof, we say, suppose there's a U like this,
Right.
then, assuming there's a U like that, I can find a relation amongst the epsilons. I don't know what it is, but whatever it does happen to be, it would still contradict my hypothesis on the epsilons.
Right, and then what do you do?
Well, then I say proof by contradiction and finish.
It's not necessary to satisfy that condition.
Like I said, it's not. It's sufficient.
Right, but you were just saying that
Now I'm saying it's a feature of the proof. It's a proof by contradiction, and assuming
I
existence
don't
of
see
this.
the contradiction. That's
Well,
what I'm
you'd
asking.
have to read the paper, I think. Okay. I'm
Just
about
from
2
the
slides
logic,
away.
just from the logic, I don't mean the
Okay.
details.
Yeah. Let's go over it. I think the proof is logically correct, but. Okay. So let me tell you a little bit about how we got to our main result. That's purely just within the sigma delta Galois theory. What happens is that we understand second order linear operator equations well enough, and this kind of thing happens nearly every time. In the difference case, there are a few more possibilities than in other theories that you might have seen before. And the point is that here, there are three possibilities for what the differential Galois group could be. The first is that it's supertriangular, and I'll mention again that that happens exactly when there is a solution to the Riccati equation, and the other two possibilities are that it's so-called irreducible and primitive, or finally that it contains all of SL2. And saying that there's no solution to Riccati is saying that the first case can't happen. Okay, so that's what the first condition does for us. The second condition, it turns out that this telescoper for the d log of b, if it existed, it would be controlling exactly what the image of the determinant of the Galois group as a subgroup of GM would be, and that telescoper would be exactly the linear differential operator defining this differential subgroup of GM as in Cassidy's classification. Okay, so saying that there's no telescoper is saying that the image of the determinant is really the whole multiplicative group. And what happens is that if you rule out the first case where G is supertriangular, then knowing that the determinant is everything is enough to say that the Galois group, whatever it is large enough to force any non-zero solution by itself to be differentially transcendental. So yeah, I think I'll stop here. Thank you very much for your attention.
So can you put back the slide on the main theorem again, on the group condition?
So I'm still not sure what you mean by the group condition. There's this theorem and then the application to the function.
No, the result that says that if the only multiplicative relation is generated by the given. Right. So you said that if the Riccati equation has a solution, then you violate this hypothesis. Is that correct?
That's correct.
So if you violate this hypothesis, what conclusion can you get?
None, because I don't know exactly how I violated. Like it's not that from saying that a solution to Riccati exists. Dreyfus and Rock came up with conditions that are complicated, and that's why I did not write them down.
Okay.
But you have certain inequalities between divisors together with certain things that have to happen when you evaluate the divisors.
No. I'm not questioning why that hypothesis.
I'm answering your question. So some of their conditions mean that.
So if you make an assumption that the Riccati equation has a solution, is that correct?
Right.
Okay. And then from that, you prove that there exists some multiplicative relation which is not generated by 1. Is that correct?
That's correct.
So how do you apply this theorem to that to get a contradiction?
This is a proof of
No, wait. A proof of what?
that.
Oh, that's a proof of this,
Yes.
not a proof of the other result.
No.
No.
Ah,
This is a consequence of the main result. So what happens is that when I assume that there's a solution to Riccati, then Dreyfus and Rock, their conditions.
So you also assume that epsilon z is differential algebraic.
That the epsilons are numbers. They don't get to be
No, the epsilon z is differential algebraic.
epsilon z. Oh, this.
Yeah. Is that in the proof? Then you start with saying that if epsilon of z is differential algebraic, then it violates the hypothesis.
No, we don't have that, and we don't know that.
You don't know that.
No.
But that's equivalent to your theorem, no?
No.
That's a contrapositive, no?
The hypothesis of the theorem doesn't apply because he's got a relation.
You got the relation.
Okay, so fair enough.
Yeah, but
If
I don't know. Could you just sketch the logic step of your proof of this theorem?
okay, are you willing to grant me our main results?
What?
We have a main result that's purely Galois theoretic, and then we applied it to show this.
Sorry. When you are sketching the proof, are you sketching the proof of this theorem? or
No,
you
I
sketching
sketched the proof of the main result in Galois
So
theory.
you assume this theorem already, right?
No.
No, this is a consequence of the main result.
Oh, it is a consequence.
Yes.
Oh, okay. All right.
Okay.
All right about that. Then.
Are there any I thought.
Yeah, sorry. I vaguely remember that this elliptic hypergeometric functions, they also arise as just usual elliptic functions as integrals of something, right?
Yes.
Is it true? So would it be the like easiest motivation? Like you want to compute integral? Here you go. I think they're just complicated integrals that people like compute integrals that just express in terms of these functions. But I'm not sure.
Are you saying that these appear in computation of integrals? Or
Yes, the functions
these ones.
Carlos was talking about, this elliptic hypergeometric, because I didn't talk basically none of them.
Oh, that's great. So you're actually.
I think that this is what he mentioned there, but this just was 2 years ago.
Yeah. So my understanding is, on the one hand, the elliptic hypergeometric functions themselves are defined as a complicated looking integral involving these elliptic gamma functions. But on the other hand, because of the nice properties that they happen to have, which they prove after the definition is set down, you can use them to compute other things that you may care about. For example, coming from representation theory, so some of these character formulas are written in terms of integrals, and because you know enough about them, they have to be related by the elliptic hypergeometric functions somehow. So there are applications like this, but I'm very deeply unfamiliar with what exactly they are.
I see. So, but in general, they are connected to certain integrals, and in principle, they can be used to compute these integrals or to manipulate these integrals.
Yeah.
Okay.
And that's part of the reason why mainly the main reason why the math physicists care. They're trying to do physics, and then they get equations, and some integrals happen to be important to them, and these functions are meant to help them.
I see.
And so far they've been successful, and they're hoping to be even more successful in the future.
Okay.
With your help.
Yes. I hope they can use my help. We'll see. Yes.
So the definition is really of, these are for PQ elliptic hypergeometric functions, that the P and the Q are somehow specified in advance.
That's right.
So, but they don't have any particular preference for any P's and any Q's.
I don't believe so. They ask for both of them to have norms strictly less than 1 for analytic reasons. But I'll also say, just for clarity, I know that this is not what you're asking, but they're also of the P and the Q here are different from each other.
Right, because of the intersection.
Yeah, it's like P gives you the curve and Q gives you the point on the curve. Right. You know, in this survey that I read, one of the things that they hope to be able to do in the future is to be able to make sense of things when the norm is maybe not less than 1, but maybe exactly equal to 1, or possibly extend to when one of them, say the Q, is a root of unity, and he expresses as a wish that he hoped that someone will be able to.
So there's a separate theory for every P, for every pair of P that meet the conditions.
I mean, there's a moduli space of theories parameterized on P and Q. And they all end up looking the same, so the fibers are have the same shape, but they are, it's a different conversation for each choice.
So even though if I like a rational P for my choice,
that's fine.
that doesn't have anything to do with it.
Not as far as I can tell.
So then, I'm going to make
But you can't
P
have
Q.
both P and
I'm
Q
going to make the
rational.
I choose 7 of the epsilons at random, and I get one special one. Why isn't 8 the special one instead of 7?
You actually
So-
said 7 and 8 are
7 and 8 are
special,
special.
right?
7 and 8 are special.
Yeah, but I can pick
Yeah.
Pick on it.
That's right.
So-
pick 7 of them.
So part of the reason, so the short answer is I don't know, but I have some ideas about why, and part of the reason that I did not write the formula for what the F epsilon is, I could have just written down and told you, see, you can't make sense of it. But the reason I didn't do it is that actually the F epsilon is first defined with respect to a different set of parameters, T1 through T8. And then these parameters satisfy a similar but different kind of balancing condition. And then once they define the function using those T's, Then they do a reparametrization of the epsilons. And that parametrization, the first 5 epsilons have the same kind of relation to the OTs, and the last 3 don't. And I thought that it would just take too long to be like, here's some parameters. Actually, never mind. I want these other ones instead, and so I skipped the whole discussion. But I'm not sure to what extent the original T's in integral definition are interchangeable. Presumably, there, who knows if only the 8th one or the last 2 are different. But then when you get the epsilons out of the T's, the last few epsilons have a very different definition relative to the first few. So that's why-ish.
So I suppose you won't know the answer, but I would ask still, what motivates the definition of the epsilon z?
I don't know. The best I have, and I'm really just quoting, I don't have any deeper understanding of the statement, is that the integral expression that they have for the f sub epsilon mimics, according to them, the Barnes integral formula that you have for the classical elliptic, non-elliptic Gauss hypergeometric functions.
So the reason is mathematical, you're saying?
Kind of. They think that the formulas are different versions of each other, but I can't see why. But they believe this. And physicists, if the math works out,
the integral formula is very complicated too?
Pardon me?
The Barnes integral formula is very complicated too?
No, that one's nice. Enough. It's nice enough to write down.
Okay, good.
Here. That's a key question that if I got, I would write something on the board, so here goes. This is the correct board to, well, not this. So here's your, maybe I started here. This one being on space. Let's try it.
Is that
So it's 1
a
over.
2 or is that?
This is a Z with a line in the
The
middle.
first one.
This is also a 2. Line in the middle means Z, no line is 2. This is 2 again. 2 pi I, then times gamma at C divided by gamma A, gamma of B, times a longish integral. Let me put it down here. There. So it's that. It's not terrible, but already in the classical case, it's not exactly nice either. And the one for my functions here is simply just a mess. I don't know enough to be able to read it and think about what it's saying. With this one, I think I could try, but even for this one, I don't know. Okay. But this is the formula that they claim to have an analog for using elliptic gamma functions instead. And then those functions happen to be beautiful and have properties, including the fact that they satisfy my difference equation that opened the door for us to be able to say things about it.
Let me ask, the reparametrization of the elliptic curve in terms of P and the units, C star, is also the basis for work Tate did on p-adic theory of these things.
Mm-hmm.
Is there any interest in doing this kind of result in the p-adic setting?
Gosh, that's a really good question. And for once I know the answer. Yes, I am interested, but I don't know whether anyone else is. Yeah, it'd be really nice to try to do similar things in the p-adic world instead and come up with the right analogs there. But I'm not. Well, even the usually whatever you do in the p-adic world, like there's some kind of analytic version of it that you're trying to mimic. And this analytic story, it's not exactly recent, but in math time it is. It's about 20 years old. So who knows? It'd be nice to see.
I mean, Kedley might be a person to just send him a message saying, is this of interest?
Yeah. Well, I noticed you didn't call him Kieran, and I don't either. But if I run into someone who can, then I'll have them check with him.
Other questions? And let's thank speaker again.
Thank you.